We want to keep talking about order parameters and envelope equations in specifically starting to come to thinking about how do we characterize the onset of instability and what kind of determination of the dynamics can we make when a solution starts to bifurcate. What are the governing equations? Linear stability analysis would say under bifurcation that we would just have something going unstable, which would lead to exponential growth. Right, and all that tells you then the solution goes to infinity. But of course, under bifurcation, the solution doesn't go to infinity. In fact, it starts to grow potentially to another balance, another dominant balance of what the physics is dictating, so that you get some kind of new solution. Right? So we want to move beyond linear stability analysis to start to understand the evolution of the dynamics after bifurcation occurs. And we're going to do this by what's called an order parameter description and also by characterizing dominant balance physics there. I'm going to give some examples to show that as you pick different scalings and dominant balances, you can get a nice diversity of behaviors in certain types of systems. So let's go and talk about the generic idea first. The generic idea is here, right? I have some PDE, some nonlinear evolution equation, space and time, and I have some parameter mu. And the idea is as I change mu around that the dynamics changes or bifurcates. So in one regime the dynamics looks like something, and as I go through a bifurcation point, the nature of the solutions change. Okay? And so what I'd like to do is characterize at these transition points what happens. What are the instability mechanisms and what are the new dominant balance physics that occur leading me to see what I see as the manifestation of some dynamics after the bifurcation. So the idea is going to be the following, and what we're going to look at is we're going to say that my parameter mu is near some bifurcation point mu of c. So I'm going to say mu minus mu of c is small. So I'm right at the bifurcation point, and I'm going to expand that region. This is exactly what we do in perturbation theory, right? We look at these regions, we expand them. We're going to put in slow, fast, and time scale, slow scales of time and space, just like we did in the last lecture, and then start to try to understand and characterize the dynamics itself. So let's perturb from the initial conditions. So what we're going to start off with here is a very simple example of, let's say, suppose I have a trivial solution. 0 is a solution to this. Then I want to say, all right, 0, and what happens when I perturb from 0? So I have some perturbation from here, and what happens in the system is what happens if there's some value of mu of c, which when I walk mu past that, the 0 solution becomes unstable, and then I see some pattern arise in my dynamics. So that's what's going to be captured here by this u tilde, and notice what I've done. U tilde has both slow space and slow time. That's the xi and the tau variables that we introduced in the last lecture. Okay? So this is important. We're doing a multiple scale expansion in spatial temporal systems such as this, near the bifurcation point. Okay, so let me give you an example of exactly what I mean by this. So consider the following PDE. So this is some complex, it's got some fourth order differential equation here, which is, so this is fourth order diffusion. It's got a cubic, a quintic. It's got some nonlinear cubic terms that are with mixed derivatives. So it's a fairly complex equation, but it exhibits some very interesting dynamics. And what we know for sure is that the solutions to this has a trivial solution, u equals 0, that once you get past a certain parameter point, that 0 solution goes unstable, and you start to see the evolution, non-trivial evolution dynamics in the system. So what I'm going to do is I'm going to perturb about the 0 solution. And so I'm going to say u tilde, which is the perturbation around the 0 solution, also is going to have this form here, which is e to lambda t plus ikx. This is going to be my dispersion relationship when I can relate lambda and k together. Okay? And what I'm very interested in is, when is lambda, the real part, less than 0? When is it greater than 0? If it's greater than 0, it's going to be growing. If it's less than 0, it's going to be decaying. So right where lambda, the real part, is 0, is where the bifurcation occurs. Okay? That's what the dispersion relationship is telling you, is you plug this in, when you perturb around the 0 solution, you get this dependence of lambda and k, and where the real part of lambda switches from negative to positive is where the bifurcation will occur. So in fact, if you plug that in, here's what you get. Here's the equations relating lambda and k. So this is my dispersion relationship. And then I can just ask, when is lambda 0? Right? That's going to be the point at which, if I'm above 0 or below 0, this is the bifurcation point. So when you plug that in, you can actually easily solve that and say that, okay, the bifurcation point is going to happen here for k squared plus 1 squared over 4. That is where the lambda is 0. That's the bifurcation point. And this is exactly where I want to do my analysis. If I'm below this, in other words, if the parameter mu is below this, the 0 solution is stable. If I'm above this value, then the solution is unstable. So I want to go ahead and try to characterize the dynamics then. So what do? I introduce slow scales, slow time, slow space, just like what we did in the last lecture. And notice what I've done here. Tau is epsilon squared t, and c is epsilon x. So it turns out I already know what the dominant balance should be. And I should have an epsilon squared, so it's a very slow time scale. There's an epsilon squared there. And x is just epsilon x. If you didn't know this ahead of time, and you just said there's some epsilon 1, epsilon 2, by doing your dominant balance calculations, you would come to the conclusion that this was an epsilon squared and that's an epsilon. It's the only way to get non-trivial balances or anything that's going to make sense. I've already done that ahead of time, so I already know what the scaling should be. Just like I know what the scaling should be here. I'm going to perturb mu is going to be near the critical point, the mu of c, right, where the real part of the eigenvalue, real part of the time dynamics goes from negative real part 0 to positive real part 0. That's mu of c, plus epsilon squared rho. This is the correction. And again, an epsilon squared, I found that through dominant balance. So there's so much algebra I'm skipping here that you have to walk through and characterize, but it's just algebra. And it's just a matter of lining up what should these actually be. And then when you put in these dominant balance scalings that we have here, the epsilon squared here, epsilon squared there, epsilon there, what you find for the slow evolution equations, right, which is satisfying the Fredholm alternative theorem, is this is the order parameter description. In other words, this is the evolution dynamics that happens after that bifurcation occurs. What we have here is something that looks like the Fisher-Kolmogorov equation. In other words, locally, when I go through that bifurcation, the dominant balance physics is this Fisher-Kolmogorov equation. And that's exactly what we were able to do here for getting an envelope description of the instability of this equation of the trivial branches of solution. So yes, there's a lot of terms here, but at the instability point, at that bifurcation of the trivial solution, this is the dominant balance physics that happens. This is your order parameter description of that instability. I don't need all the other terms. It's dominated by a cubic. There's no quintic in here. It's also dominated by a diffusion process, not a fourth order diffusion process, or any of these other mixing terms that were in there. So this is an example of how it's very much, this is the normal form of that bifurcation. Remember, the equations itself can be much more complicated, but when I'm looking here at this spot, this is the dominant balance. This is the normal form of that bifurcation that happens and the onset of instability there. Okay? So in other words, the solutions just don't grow to infinity. Like when you do a linear stability analysis, you say, oh, look, these solutions are growing. That's fine, but this tells you exactly how they're growing. In fact, they don't go to infinity. They go, this is what they go to, this branch of solutions here, which is this Fisher-Kolmogorov equation. Let me give you another example. And again, there's a lot of algebra involved with this example, but I'm going to just highlight for you the process is the same throughout. I'm just going to highlight the results for you in this case. So this example it's called an optical parametric oscillator. It's a coupled PDE system. So they're coupled through the complex conjugate. I have a field U and a field V. And so here are their dynamics. This comes directly from optics. And so U is coupled to its complex conjugate and the V field. It's also coupled to itself, and it's got some diffraction terms. These are what these terms are here. And V is coupled to U squared. And so this is a really interesting equation for light fields at two different frequencies that interact in some nonlinear material. So you can derive these equations directly from Maxwell's equations as a reduction. And so the question is, can we start to understand some of the dynamics that are observed in these spatial-temporal systems? In fact, this has a lot of very interesting physics that is observed in this. And so what we want to start to understand is the bifurcation from the trivial solution. So there is a solution where U0 is 0 and V is equal to S, and S is just some forcing of the system. S is essentially going to act like my bifurcation parameter, okay? And so V is some constant, which is dependent upon that S, and U equals 0. So this is my trivial solution. And what I want to ask is, at what point do I make S big enough that this solution goes unstable? And then what happens to my optical fields past that point? So we can actually compute the bifurcation point, and this again is just the point when I look at my dispersion relationship. When does the e to lambda t, when does that lambda value, its real part, go from negative to positive? And it's at this value here. S of c is equal to alpha plus I delta 2, 1 plus I delta 1. Okay? Delta 1 and delta 2 are called detuning parameters. And again, this comes right from deriving this from Maxwell's equations. Not so relevant here unless you are interested in this problem, but then there's reference to it in the notes. You can follow up on this problem if you want, and also follow up with it and see all the gory details of everything that we're going to do here, because I'm just going to give a summary of this. Because the summary is just really going for the philosophical pieces that we have. We have a spatial temporal system, we have a given solution, in this case a trivial solution, and we have a bifurcation point. And what we want to understand is what happens when it goes unstable, and I know where it goes unstable, so I want to do an expansion near this bifurcation point to come up with a dominant balance physics modeling paradigm that kind of highlights for me the key physics that are driving the instability. Because solutions aren't going to infinity. Solutions are going to some new solution state that I want to get sort of what the right dominant balance physics is for that new solution state. So as before, we introduce slow space, slow time scales. And actually what I'm going to do here is I'm going to actually introduce 2 slow time scales and 2 slow space scales. Okay? So the slow time scales are epsilon squared t and epsilon to the 4th t. And this slow scale is epsilon x, and this slow scale is epsilon squared x. And it turns out, depending upon the parameters of this system, you're going to get different dominant balance physics that occurs near the bifurcation point. In fact, your choice of delta 1 and delta 2 are going to determine a great deal of what kind of behaviors you can get out of this system. So here's the idea. We're going to perturb the system, u and v. It's near the trivial state plus some epsilon amount. This is my linear stability analysis. V is going to be the solution, this is the constant solution, plus epsilon squared v. And again, I know these dominant balances because you can actually go capture them to make sure that you get the right dominant balance physics. I look near the bifurcation point. So S minus S of C is epsilon squared C and corrections. So I'm expanding with slow space time scales near the bifurcation point. Okay? That's all I'm going to ever do in these order parameter descriptions. Find the bifurcation point, define slow and space time scales there. You have to do your dominant balance, make sure you get the right scalings, and this is what I'm doing here. And I haven't shown you how I did it, but you're going to plug this in, and you could put in epsilon to some generic power and epsilon to some other generic power, and then you would figure out that has to be squared, that has to be to the 1st power. Otherwise, you get nonsense in your solutions. So you expand this. So you take this, you put it into your governing equations, expand everything, and here's the kind of things you get. Here's your leading order term, here's the epsilon squared terms, epsilon fourth terms. That's for the first equation. Here's your second equation. Here's your order 1 terms, order epsilon terms, order epsilon fourth terms. So you get a lot of different terms in here. And what I'm going to do, I'm going to impose Fredholm alternative. So the right-hand side forcing terms have to be orthogonal to the null space of the adjoint operator. That's how I'm going to get the slow evolutions. We've seen this now in our previous 2 lectures, and we also saw it throughout when we were doing perturbation theory. How do you satisfy Fredholm alternative? That's going to enforce the evolution dynamics that you're going to get out of these equations, the slow evolution dynamics. There's some more manipulations algebraically that happen here. You can write U in terms of a perturbation expansion, in terms of, V in terms of perturbation expansion of U, and then you can also write U star in terms of U from this formulation, from those equations. And those are going to be all necessary in your perturbation expansions. And what you end up going to get for your right-hand side terms at order epsilon squared, I'm just summarizing this here, is this here is what pops up at epsilon squared. This is what pops up epsilon fourth and higher order terms. Like I said, there's a lot of algebra in putting this together, but it's not so bad. But I'm not going to work it out here on the light board for you or even show it. I'm just going to highlight it because this is what we have. And we also have this relationship here at leading order, which is, this is in some sense our null space that we have to consider. Okay, so once you have your leading order solution, its null space, the corrections, and all this expansion, then you can start playing around with the solvability conditions. Now you say, well, if I know what the null space is of the adjoint operator, that means that the right-hand side forcing term has to be orthogonal to it. And that orthogonality condition is what's going to give us, what I'm going to show you, is 3 different balances. And it all depends on how you pick the parameters delta 1 and delta 2. So for instance here, the first balance is the easiest balance, and it comes out to be some kind of Fisher-Kolmogorov equation. So when the onset of instability, in other words, for the optical parametric oscillator, is this Fisher-Kolmogorov equation, where I've rescaled everything. So here's what the U field looks like. Here's what the slope C looks like, and here's what gamma looks like. And in this case, delta 1 and delta 2, those detuning parameters, are both order 1 quantities. And if they're both order 1 quantities, this is, in fact, the dominant balance physics. Remember, these parameters don't have to be order 1. I could, in fact, have these detuning parameters be order epsilon squared, for instance. And in fact, that's going to allow us to get different balances for the resulting envelope evolution that comes on, or the order parameter description at the instability. So what a linear stability analysis would tell you is near the transition point, when you go through the bifurcation, you have a solution that just exponentially grows, which would just say that the solutions go to infinity. And what this tells you instead is, no, it doesn't go to infinity. By having the slow space timescales, when this starts to grow, this is, in fact, the governing equations of that growth. It's bounded, and it evolves according to this PDE. Okay? And these have some interesting solutions themselves. So this is the dominant balance physics, or the order parameter description, at that bifurcation point. There's a second balance where if those parameters delta 1, delta 2, and the bifurcations have certain, are of certain order, then you can also bring in this as the dominant balance physics, which now has a quintic term. So now notice you have a cubic and a quintic. So it's like Fisher-Kolmogorov, but now the balance brings in this quintic term. So this is another potential order parameter description, which is directly dependent upon the parameters of that optical parametric oscillator, those delta 1 and delta 2 parameters that you have in the system. Okay? A third even balance that you can bring in is when you have what's called near resonance detuning, when those delta 1 and delta 2s are order epsilon squared size. This becomes the dominant balance physics. Here it is. Look at this. This is now something like a Swift-Hohenberg type equation. You have some fourth order diffusion operator. You have a cubic, a quintic, some nonlinear cubic mixing terms with the derivatives, and this is all in this regime where you have a very specific balance of the parameters. So in other words, for this system, this optical parametric oscillator, there's at least 3 dominant balances that can occur in the system, which are all physics-based balances depending upon the detuning parameters and how close you are to that bifurcation. And so this gives you this very rich way to study and characterize the dynamics that happen. Not just it's unstable, it grows, but when it grows, it evolves according to this equation or the other 2 that I showed you. All are possible depending upon the parameters that you have in the system. And all this is to say, what this is allowing you to do is to start thinking what the order parameters are allowing you to do is it gives you the dependence of the dynamics on your asymptotics, scalings, and balances, right? So I give you a problem, and depending upon the size of the parameters, it's going to generate different kind of dynamical evolution depending upon those parameters. And this is the dominant balance physics that occurs at the instability, or the normal form of that instability in some sense. So this highlights a methodology to get at that. It's not enough here just to say, oh, it's unstable, because when it goes unstable, it just goes to some new solutions. The question is, so nothing's going to infinity or blowing up, which is what the linear stability would tell you. What this says is, as this thing goes unstable, this is the dominant balance physics that carries it into the new parameter regime. And so order parameters become these very important methods for studying pattern-forming systems because they are the description of what occurs through a bifurcation point and connecting one side of the bifurcation to the other side of the bifurcation where you have solutions that are finite and have dynamics instead of just things blow up and go to infinity like you would get in a linear stability analysis. So again, slow space-time scales, that's what we're relying on for this description, and an approximation near that bifurcation point. Do your dominant balance physics, write down that envelope equation, which is coming directly from Fredholm alternative, and now you have this way of understanding a system that's beyond just your standard linear stability analysis.